Welcome. We're going to keep going with logic, and we're actually going to talk a little bit more about valid, invalid arguments. So we've been building arguments up to this point in time by doing a lot of things. So specifically, an argument is going to be a sequence of statements or so all these things that we've been building, these predicates, we're gonna now take those together, and we're gonna in propositions we're gonna put them together, and we're now gonna make one giant argument. So we're gonna get something called a therefore. So there's a couple things that are really important in this process. One is we're gonna use this symbol a lot for therefore. That's three little dots that make a little triangle. This is the same thing as saying therefore. So if you see that, it literally reads as therefore. Also, determining if something is valid does not mean if any of the statements are actually true or false. It simply means if all the premises, all the things before the therefore are true, then the conclusion is also true, always. If there's even one example where that breaks, then we throw it out. So you have to be careful to not rely on, what do I know? Oh, that doesn't make any sense. No. It's not about, because computers, especially all my computer science people, we deal with things that don't make sense. A computer doesn't know logic. It just knows that you built up a statement for it. So if you built an invalid argument, you are the problem, not it. It's not its fault that it can't interpret. So we have to be very careful. Mathematicians, it's the same thing. You're going to build things that you have to understand all the details of, and therefore sometimes being concerned about, oh, that doesn't make any sense. I don't really understand that part. Well, that's not the point. You have to understand that this leads to that, and that's how we get to the end point. So a couple things to test for is, one, we need to look at what are all the different premises. We do kind of a truth table. That's one thing a lot of people like to do. You don't have to do a truth table, but the question is, okay, a truth table to show that all the premises lead to the conclusion. Can we very say that if all the premises are true, then we get the conclusion? Yes or no? And it mentions a row here. A row in the truth table, which all the premises are true, is called a critical row. That's pretty much the row the only row we care about. If the conclusion is false, then we got a problem. So we have to make sure we are working our way through this and understanding how these different ideas work. All right, so again, we're going to make a table. We're going to annotate the table with sentence of explanation. So it's not just making a table. We're also going to use words. So here is an example. Let's just kind of deal with this for a second. I have P implies Q and not R. Q implies P, P implies Q or not R. Q implies P and R. Therefore, P implies R. So I'm going to try to figure out this thing. What we can do is literally build a truth table that looks like this. I have P, I have Q, I have R, I have not R. Remember, this is my conclusion, and these are my premises. So I had to do all of these first groupings because they led me to get the premise situation. So now coming through here, you can see the highlighted rows are the ones that are true. If this is true and this is true, this is true. And again, P implies R. What I have to do is come back here and P, R. Well, this is true and this is false, so this has to be false. For this one row, it fails. All it takes is one row to fail, and it is automatically an invalid argument. Again, you don't even have to know what P, Q, and not R are. Sorry, no pun intended. But you need to be able to utilize them over and over. Now, some of the most famous versions of this are something called modus ponens and modus tollens. Those are those are Latin phrases. They're based on when you have two premises, like here, where I have if P, then Q, and P is right, and then we get Q as the final result. This is called a syllogism. In this situation, this first one is called the major premise, second one is minor premise. Truthfully, I don't care if you memorize that or not. This is the bigger idea is this makes sense logically. You need to understand how logic works You don't need to memorize what is modus ponens, what's modus tollens, all these other things. I'm not going to put that on any test. That's not really what you need to walk away from the class. The bigger thing you can walk away from is a valid argument or not a valid argument is going to be the bigger thing. So this is one example. So let's actually look at a real world summation. The sum of the digits here is divisible by 3, then that number is divisible by 3. The sum of the digits is divisible by 3, therefore it is divisible by 3. So this is an if-then. So I gave an if-then, and then I stated that the if part was true, therefore the then part had to be true. That is how this works. And again, if you did a truth table, this would come out super easy to see. Modus ponens or modus tollens is a fill-in-the-blank argument. So in other words, here I have an if. Let me just kind of actually do a highlighter. So I'm going to have if there are more pigeons than there are pigeonholes, then there are 2 pigeons in the same hole. At least 2 pigeons in the same hole. And then it says there are more pigeons in the pigeonholes. What can we conclude right here? Hopefully you're saying that there is at least 2 pigeons in a pigeon in each roost hole. By the way, this is a classic concept from discrete math called the pigeonhole principle. I'll explain what that means later on when we actually use it, but it's a really great and powerful tool. All right. Then we get into this next one where this is divisible by 6, then it is divisible by 3. That should make sense. And I'm telling you that it is not divisible by 3. Huh. Well, notice I just made the then part false. If the then part is false, what has to be, what do we know about this part? It also must be false, because that actually is by using the idea of modus tollens, or better is the sorry, I'm not breathing. It's the idea of doing the contrapositive. So because we actually could flip the order, remember, if I flip the order and negate them, it's the same thing. So saying something is not divisible by 3 is the same thing as saying it is divisible by 6. Sorry, it is not divisible by 6. Ugh. So if it's not divisible by 3, then it's not divisible by 6. Well, so we can flip them the other way around. All right. Let's talk about some other valid argument forms that we can infer stuff. Inference just means that they lead us to the same conclusion using deductive reasoning. So if P is true, then P or Q has to be true. That's just a generalization. In other words, if something is true, then I can say it's true or something else. A good example, I really like this on this next slide, is we have Anton. And Anton is a junior. Therefore, we could say that Anton's a junior or senior. I know you're like, what do I care? Well, the reason being, if I know that something is true, then I can say that someone actually belongs to a much more general group. If they already belong to a smaller subset of this group, I can say they belong to the bigger group. This is why this is useful for a lot of different situations. All right. The other one is the opposite direction. So generalization is we take one thing and we go to 2. Notice that this one was an or generalization. Specialization is an and. If I have an and statement, remember this is only true if P and Q are both true. Therefore, if this original statement is true, then we know that P has to be true. Boom, done. We also know that Q has to be true. Boom, done. Specializations is taking an and simplifying. Again, here's one where Anna knows numerical analysis and Anna knows graph algorithms. Therefore, we can say that she knows graph algorithms. Another one would be, suppose that I tell you that a student in this class is taking discrete math and they're taking, I don't know, calculus 3. Well, then we can definitively say that they are taking discrete math. So it doesn't seem like this matters that much, but this is actually used in much more general things. And we're going to get to mathematical proofs later on in this class Yes, that is part of the outcomes of this class we're supposed to do. It's not a huge part, but it is something we are supposed to put some time and effort into. All right, so here's another one. This is called elimination. So if I have an or statement, P or Q, and then I connect it with the not Q. So pretty much I'm just saying, remember, P or Q is true. If P is true and Q is true, P is Q, Q is false, P is false, Q is true. Well, this statement right here is going to also be true only when Q is false. Well, that means up here Q had to be false, which means that this is only true if it is also the true statement. That's why we get this here. So an or statement allows us to have one or the other without, we don't necessarily, we're doing an or, and then I'm eliminating essentially one by saying it's not true. So down here has an example of x minus 3 equals 0 or x plus 2 equals 0. Well, we can rule one out because obviously if x is not -2, then we throw out the first case. We can simply conclude that x minus 3 equals 0 and solve that, and you realize x equals 3. So this is the idea. Now, you did this in algebra, you wrote stuff like this when you factored. We are going to use that again later on in this class. Heads up, fair warning. All right. Now, here's another one. P goes to Q and Q goes to R, so that P goes to R. This is called transitivity. And transitivity is a property that's going to come up many times later on. The idea is that if the relationship between P and Q exists, and then Q and R exists, then the relationship from P to R exists. Again, this statement is true in lots of different situations. If P is false, well, then it doesn't matter. But if P is false down here, it also doesn't matter as well. So I could have them be false, and it doesn't really matter. If P is true, then Q has to be true. If Q is true right here, then R has to be true, which means, well, that R has to be true down here. So that's how we kind of get this idea that it naturally lends us to this. Again, you don't need to remember the word, transitivity, that word will come back up, but you don't need to remember this in all situations. So again, let's do an example. If n is divisible by 18, then n is divisible by 9. So let's take some number, an integer, it's divisible by 18. Then it's divisible by 9. If it's divisible by 9, then the sum of its digits is divisible by 9. In case you don't know, it's called the rule of nines. So therefore, we can say that if a number is divisible by 18, then the sum of its digits must be divisible by 9. It's really cool. I'd add one little detail, namely the fact that it's also an even number. Other than that, we're great. All right. Another one is proof by division into cases. Ooh, this one's kind of tricky. So we have the first statement is P or Q. So remember, at least one of them has to be true. Possibly both, but at least one. So if P is true, then the second line automatically tells us that R has to be true. Boom, we're done. If P is not true, well, then Q is true. Come the second line, boom, we're done. So as long as these are all true, then automatically we have to get R. So if X is a positive or X is negative, if X is positive, then X squared is bigger than 0. If X is negative, then X squared is still bigger than 0. So X squared is bigger than 0. Notice that I excluded 0 because 0 is neither negative or positive. I'm just going to move on from this. All right. We also can use further complex deduction, meaning I can put together a bunch of things. So here's a problem. I kind of love these kind of problems. I don't know about the rest of you. I love logic puzzles. I actually do them for fun. Let's say you're about to leave for class in the morning and you discover you don't have your glasses. You know that the following statements are true. If I was reading my class notes in the kitchen, my glasses are on the kitchen table. If my glasses are on the kitchen table, then I saw them at breakfast. And C, I did not see them at breakfast. So I have more information for you, but let's just pause right there. What can we simply say right now about this? Well, This part, I did not see my glasses at breakfast. We take the previous statement, and by modus tollens, it actually lets me go backwards and say, well, then my glasses are not on the kitchen table, because I negated the latter part that I saw them at breakfast. So that negates if I negate the then, it negates the if. But if this is my glasses are on the kitchen table, it negates the then in part A, which negates that I was reading my class notes in the kitchen. So right now, from this information, I can say that I was not reading my class notes in the kitchen. My glasses are not on the table. Those are a couple things I can conclude right now. If I was reading my class notes in the living room or I was reading them in the kitchen, well, one of these has to be true. So, because at least one of them, potentially both, but if this part, because my class notes, we know they're not in the kitchen, that means I was reading in the living room. Come to part E, if I was reading my class notes in the living room, then my glasses are on the coffee table. Where are my glasses? They're on the coffee table. So we can do this process by breaking this all the way out and working our way through it logically. So this is logic I just explained to you. Let's see, your book does this really nice thing where it turns each of those statements into a variable. RK is reading notes in the kitchen. GK, glasses on the kitchen table. SB, saw them at breakfast. RL, reading in the living room. GC, glasses on the coffee table. All right, so RK implies GC. That's what part A told us. Then we get GK implies SB. So from there, because RK implies GK and GK implies SB, then RK implies SB. So we now get this new statement right here. So I took the first two statements, I smashed them into one. RK implies SB. I then added the next layer, which is not SB, which gives me not RK by modus tollens. Remember, that's contrapositive, modus tollens, whichever one you want to go with on that. And then I have RL or RK. Well, if it's not RK, because we get that from up here, then it has to be RL. And then we can come to RL implies GC, and RL is true, so that we're in GC. They're on the coffee table. This is how you can literally build this out if you want to write it down. Another way to write down is just like I said. Well, let's break this out. We know this, so by this, and actually the things I said, you would simply write out in great detail, or you could use a symbolic logic notation that we just did right here. Both are valid ways to work through something to come to a conclusion based on the information you have. So this is where one of the abilities you should have for this class is to come to a logical conclusion based on some given information. You also need to know if something is true or not. And that's where we get into something called fallacies. A fallacy is essentially a logical error. It gives us an invalid argument. It means that we assumed something, circular logic, we jump to a conclusion. There's a lot of really bad fallacies out there. You can Google and go down a whole hole. We're going to talk about a couple of them in here, specifically the converse error and the inverse error. And they're ones that people mess up with a lot. And so again, making a truth table and finding at least one critical row where they're all true, but the conclusion is false, is one way you can show it's. Another way is just a same form of truth and false conclusion. So let's just look at an example, because I really want to show this. If Zeke is a cheater, then Zeke sits in the back row. Zeke sits in the back row. Therefore, Zeke is a cheater. Now, you and I can look at this and be like, no. We don't have enough information to say that he's a cheater. He could be a cheater. He also could just like to sit in the back row. Maybe there's a girl back there he wants to sit next to, or a boy, I don't know. Maybe there's someone just back there he really wants to sit by. Maybe he's more comfortable in the back row and doesn't want to get called on. I don't know. I don't know anything about Zeke. But what I do know is that I cannot definitively say that he is a cheater, because there is possible that, so this first statement could be false and this could be true. Because remember, this first line, if then, is true if it is false true. Therefore, we cannot, this sometimes also is called assuming the conclusion. So when we get to the conclusion, we cannot work our way backwards. That's why it's called the converse error, because the converse is when you flip the order. There's lots of different names for this error. The idea is that you cannot flip it and go backwards. All right. More general form of this, if I said P implies Q, Q is true, then P is true. I can't say that. So again, we have to be very careful about our logic. By the way, this is a classic one, and your book is like, everyone knows this one. No, they don't. To be honest, this is the one I see is the most problematic error that a lot of people do because they overassume things. Another one is this. So P implies Q, not P, therefore not Q. And the example up here is if two vertices are adjacent, then they do not have the same color. These two vertices are not adjacent. These two vertices have the same color. No, again, you're making too much of an assumption. Remember, P could be false and Q can still be true in an if-then statement. So because of that, if-then statements are really, really hard. The only thing we can do with an if-then statement in reality is if P is true, then I have something to do. And if not Q is true, which really means that in both these situations is the only time that we can really come to a valid conclusion about our situation. All right. So here's another one. If Canada is north of the United States, then temperatures in Canada never rise above freezing. Canada is north of the United States. Temperatures in Canada never rise above freezing. So the thing about this is that in reality, logically, this is valid because we confirmed the fact that Canada is north of the United States. So therefore, we get the then part, which is our conclusion. Now, the problem with this is that you and I can look at this and be like, no, Canada does get above freezing just because it's north. It's not a problem. If there's any Canadians in here, I apologize. But this is an example to show that sometimes we focus on whether or not something is true rather than the question of does it have an actual answer? Conversely, here's another one. An argument, if New York is a big city, then New York has tall buildings. New York has tall buildings, therefore New York is a big city. Now, the conclusion, New York is a big city, is true, but the logic here is flawed because we confirmed the then part, New York has tall buildings, to get the if part. It doesn't work that way. So we have to be very, very careful. This what gets into the idea known as sound versus unsound. Again, I'm not going to spend a lot of time on this because sound is not as important as valid. Because if you don't understand valid, then we have a slight problem. A sound argument is if it is valid and the premises are true. So it's much stronger. So you can't have a sound argument that is invalid. So even this past one, while the conclusion was true, was actually not sound. That's the idea. Okay. Now let's talk a little bit about. Let's end with contradictions and valid arguments. Well, contradiction rules. If you can show that P is false, this leads logically to a contradiction. And this leads to. So this idea is in other words, if I say not P takes me to C, something that's not true, then this means that so if C is, remember, a contradiction, something is always false. So if not P always leads to something that is false, then the not P has to be false, which actually means that P has to be true. In a truth table, here's P and not P, and remember, contradiction's always false. So this statement's true, but if this statement's true, this is what we do later on when we get to proofs called the proofs by contradiction. An example is a classic one of two groups on an island, knights and knaves. Knights always tell the truth, knaves always lie. You want to know something about them. A says B is a knight. B says A and I are of opposite type. what are A and B? Now, we actually don't have a ton of information here, but because you can't assume, let's quick question, did you assume in your brain that they were both different types? So either they're both lying or they're both telling the truth. So let's think about this for a quick second. And I will also show you, I'll come to this conclusion in just a second. If B is telling the truth, then A is also telling the truth. Because if B is telling the truth that they're opposite types, if he's telling the truth, that means he's a knight, and that means A is lying. But that means that A, who said that B is a knight, is actually lying. So that means that B must be a knave. So B cannot be telling the truth. Boom. That's not true. Okay, so we now know that B must be lying. All right, so if A is telling the truth, now if B is lying, that means they're the same type. So if A says that B is a knight, well, then they're both knights. Again, we have a contradiction. So the only way this is possible if they're both knaves. We could also do the opposite. We start with, let's suppose that A is a knight. So we're going to suppose one thing. We're going to show that it goes to a contradiction, which means the opposite must be true. So if we say that A is a knight, that means that A is telling the truth, which means B is also a knight. That means that B is saying is true. That means they're opposite types, but that's a contradiction. So therefore, what we suppose, which is A is a knight, is false. So this is one of the few times we make an assumption, but we're really using an assumption very strategically to actually show that it's false. Now, since A is a knave, now we know that A is false. So that means that B is not a knight, which means B must be a knave, and that's pretty easy. All right. I hope that's enough for you. Let me know what questions you got.